In this pincast, we'll take a look at the difference between real and ideal batteries. So typically, we assume that batteries are ideal batteries. That means that if we take a look at the battery itself, here's my battery, we'll make this the positive terminal, this the negative. We have a current I going through here. That the ideal battery has no internal resistance, which we'll denote as a lowercase r. So that means that the potential difference for an ideal battery, so the potential difference of the battery will exactly equal the EMF. However, for a real battery, we have our source of EMF, but there's also a small resistance in here. So again, denoted as lowercase r. So then taking a look at the potential difference across the terminals of the battery in this instance, that is going to equal the EMF minus the current going through the battery times that internal resistance. So delta V bat is what we call the terminal voltage. For an ideal battery, that terminal voltage is equal to the EMF. For a real battery, that terminal voltage is equal to the EMF minus the current going through times the internal resistance. And this is going to be less, approaching equal to the EMF depending on the size of that internal resistance. So in a real battery, when the current is 0, then the terminal voltage is equal to the EMF. But when you actually have current flowing through, the terminal voltage will decrease. So, when in use, that internal resistance R is in series with the equivalent resistance R for the rest of the circuit. So, if we want to figure out what the current is, the equivalent resistance of the entire circuit, including the internal resistance, is the resistance of the circuit plus the internal resistance. So if you have more than one resistor in your circuit, here, this would be the equivalent resistance not including the internal resistance. So normally, R is much, much smaller than the resistance of the rest of the circuit, so we can ignore its small effect. But in this example, we'll go ahead and take a look at how much it might affect things. So let's start with a circuit. We'll have my source of EMF here, a small internal resistance, my resistor R, and again, all of this is inside the battery. So the potential difference across capital R, so the potential difference across my large resistor R is going to be equal to the current times R. We'll plug in our value from the current that we derived just above. So that's the EMF divided by the sum of the circuit resistance plus the internal resistance. Again, this is multiplied by R. So we can rewrite this like this. So this is the potential difference across the resistor. Now if we want to look at the potential difference across the terminals of the battery, again we call that V sub bat, That's equal to the EMF minus the current times my internal resistance. I'll plug in for my current using what we derived before. And I'll start to simplify this. So I can pull out the EMF. I want to try and get a common denominator here inside the parentheses. So I'll multiply by 1 on top and bottom by R plus capital R plus little r. So now I can sum these things up with a common denominator. We'll notice that my little r's here cancel, leaving me with the capital R. So, as expected, the terminal voltage, so the potential difference across the terminals of the battery, equals the potential difference across the resistor, which is what we'd expect since those are the only components of this particular circuit. So, what happens when R equals 0? So capital R, the resistance of the circuit. This is called a short circuit, and it's what some of the students did during our Light the Bulb mini lab in class. It explains why the bulbs got hot. So let's start with our battery again. So our internal resistance, little r, our EMF inside the battery. And we've connected the two terminals of the battery, the positive and the negative terminal, and we have a current going through our wire. But notice we have no resistance in the wire of the circuit. The only elements in the circuit are inside the battery itself. So we're going to label this current I sub short. So let's take a look at what this current might be. So using our equation from before, we've got the EMF over the sum of the two resistors, but my capital R is not there, so that goes to 0. So now I have EMF over the internal resistance. So again, we're going to label this as I sub short. So basically, what this tells me is the maximum possible current that the battery can produce. This also is assuming that we're using an ideal wire. If we had an ideal battery shorted with an ideal wire, that would create an infinite current, which of course isn't possible. But we are assuming that there's no resistance in the wire itself. So let's do an example. Say we have a AA battery that has an EMF of 1.5 volts and an internal resistance of about 1/10 of an ohm. So what is our short current here? What's the maximum possible current that this battery can produce? So that's going to be 1.5 volts over 0.1 ohms, which gives me 15 amps. So when you connect a wire across the battery, a AA battery, as some students did in lab, it's producing a current as fast as it can. Normally the power created by the battery is dissipated by the resistor in the circuit, to light the bulb, for example. But with only internal resistance, the power is dissipated inside the battery itself. So how much power was this battery dissipating when we shorted it out? So power is equal to current squared times our internal resistance. So our maximum current possible was 15 amps. Our internal resistance is 0.1 ohms. If you plug this in, you'll find that that should come to 22.5 watts. So that 22.5 watts is the heat that you felt. So AA batteries are designed with a high enough internal resistance so that they don't explode if you happen to short them out. Car batteries, on the other hand, are not. So let's take a look at what this might be for a car battery. So for a car battery, they have an EMF of 12 volts and an internal resistance of 0.02 ohms. So the short current inside a car battery is about 600 amps. Now, if we short this out, again, the battery is going to be working as fast as it possibly can to produce its maximum current. So all that power that's created by the battery has to be dissipated somewhere, but the problem is it's going to be dissipated internally, inside the battery itself, because that's the only resistor that's available to dissipate the current. So if we calculate the power here, plug in our 600 amps for current, multiply by our internal resistance, and we find this is 7,200 watts. That is easily enough power to explode the battery. So, moral of the story is, it was okay when you shorted out the AA battery in class, it just got a little warm. Do not try and short out a car battery. That's very, very, very dangerous. So make sure you know what you're doing when you're trying to jumpstart your car.